All right, let's just take this next question for example. This is where the things which we observed, that first thing we learned in this previous section is about that we need to use states to find cycle into a graph using depth first search, right? Second thing, I just talked about reversal of graph, but we did not went into depth of how actually it can help us solving some of the problems, right? So I'm taking another small question, small stepping stone, so that we understand these, I would say the basics, and ultimately all these will connect when we will go into strongly connected component. So yeah, this question I found relevant. Obviously, if you just want to solve this question, that you can do easily using topology or depth first search as well. But I'll try to, what I'm trying to do is finding questions to go over the topics which ultimately build something bigger, so that we can learn strongly connected component easily. Let's go to the whiteboard first. All right, let's just take this one for example. All right, let's try this graph. The same question. So what that question was saying is, if a node, every path from any node is ultimately going to the terminal node. Terminal node means, for example, 7, that there is no route going from 7 forward, and 6, no route going from 6 anywhere. Okay, so every path from any node, if it is ultimately reaching to the terminal node, then they are calling it a safe node. So we need to find out all the safe nodes just for understanding. Obviously 7 and 6 are terminal node by themselves because path is landing here itself, right? 9 is a safe node because 9 starts from 9, you will end up at 7, and that's it, that's the destination. Same for 8, if you'll start from here, ultimately you will end up at 7. In case of 2, if you'll start from 2, this path is landing at 6, right? But there is another path which is going to 3 to 4, which is going to 6 again. But from 4, there is another path going to 5, 3, and this is rotating in circle. That means this one path from 2 will never go to 6. Means there is one path which is basically not ultimately going to the terminal node. So we can say 2 is not a safe node. Same for 3, because obviously this is in cycle. So there is one path which is going to the terminal node from 3, but every path should go to the terminal node. That's the condition in the question. Okay, so that way from this particular graph, our 6, 7, 9, 8, only these 4 nodes are your safe nodes. Okay, so these are safe nodes as per the question. Now how we'll try to, again, the intent is not to solve this question. Intent is to observe what reversal graph actually gives us, right? What is the benefit, and that we will use into a bigger concept. So coming back, if I have to do it with depth first search, normal depth first search, how will I do it? I'll start from 1. Let's suppose I'm doing DFS. Again, not reinventing the wheel, just see how basically it will happen. So what do we do in depth first search? We basically have a visited array, same our states, because whenever there is a cycle in picture, that state in visited 0, 1, 2 state which we just saw are useful for us. So I'll create a visited array here. How many vertices we are having? 1, 2, 3, 4 is there, 5, 6, 7, 8, 9. That's it, right? By default, state of every node is 0. Okay, so let's suppose we'll start with our DFS from 1. Okay, because we start from starting. So we are starting from 0. That means the state, whenever we will enter into our DFS code, the state will become 1. Okay, from 1, the one path is going to 2. So because the state of 2 right now is 0, so which is okay. That means we will go to do DFS on 2. So state of 2 will become 1 firstly. From 2 we can go to 6 and 3. Let's suppose first I'm going to 6. Okay, so I'll go to 6. Then state of 6 is 0. That means it's safe. So I'll basically will do DFS on 6, and the state of 6 will become 1. Now there is no child node from 6. Hence nothing will happen into that loop, and will come outside the loop, and we'll mark the state of 6 to completed, which will be 2. So state of 6 is 2 now. Now from recursion it will come back. So from 2 now in the loop it will go to the next child, which is 3. So right now state of 3 is 0. So we'll do DFS of it and it will become 1, right? Then from 3 we will go to 4. State of 4 is 0. It will become 1. Okay, then state of from 4, again we have 2 options. Then let's suppose I'm going to 6 first, but 6 is not 0, hence we will skip that part into the loop like we used to do earlier. We'll skip it. So next is 5. Option 5 is 0, so we'll go there and we'll mark the state to 1. From 5, when we'll do the DFS, we'll see the child is actually having 1. That means there is a cycle. So what we did earlier, if there is a cycle, we return from there itself, and we will return with the true that yes, there is a cycle. Hence it will return back from 5 to 4 saying that there is a cycle. So nothing will continue from 4. So it will come back to 3 saying there is a cycle. So it will come back to 2. That means even if there are extra paths to explore on those nodes, when you are returning true from the subchild, then we will not even explore further. We'll stop it there. So same way it will come back till 1 saying that there is a cycle, and our DFS will stop here. But the outer loop, which is calling the DFS, that is not stopped. So what it will do is it will continue for checking for the next node. So we started from 1. Now we'll go to 2. Is the state of 2 is 0? No. So DFS will not be called. Same way it will check for 3, 4, 5, everything until it will come to 7. So for 7, state of 7 is 0. So it will call the DFS on 7. So on 7, when it will come, so state is 0, it will become 1. Then there is no child to go from 7. Hence the state will become 2, and that's it. It will come back. Now our loop again will call depth first search for 8, because the state of 8 right now is 0. So when it will come here, first it will mark the state of 8 as 1. Then it will go to the next child, which is 9, and mark the state of it as 1. Then from 9, there is only one child. It will check the state of 7 is 2. So it will skip it and loop will complete. Hence for 9, there is no other path, hence state will become from 1 to 2. It will come back to the parent. From 8, there is no other child to explore. Hence the state will become from 1 to 2, and DFS will complete from here. Okay, now we are done. So what ultimately we'll do, from this visited set, we will check how many nodes actually got explored completely. That means those are our safe nodes. So that is the first way to do this one, via depth first search. This is the usual way. We haven't done any reversal, nothing yet. Okay, so this is the first way. Let's just code this one to check if our understanding is correct or not. Okay, so we are writing depth first search, where we are supposed to call with vertex v, and we will return whether there is a cycle or not. Okay, first thing we do is, in our visited array for v, we check if this is already 1, right? That means there's a cycle. So if this is already 1, we'll simply return true that yes, there is a cycle. If not, if this is already completed, in case someone is calling, if this is already 2, just return false, there is no cycle, but completed, nothing need to be done. Else what we are doing is, first thing, mark it as that I am starting exploring it, hence this is 1. Now for all the children in self dot graph of v, means all the adjacent neighbors or child, you can say, what we are going to do is we will check if by any chance self dot visited of this child is already 1, though I checked it here itself, but doesn't matter, I can check it here also, is already 1. That means I can simply return true, that yes, there is a cycle. Or when I'm doing the DFS, so self dot DFS for the child I'll do, and by any chance if any of the path, it will return true. That also means that in subpath there was a cycle, so return true from here. Do not need to explore, no need to explore anything else. If not, then loop will complete. Then what we need to do is self this vertex as done, which is a state 2 for us, and also return that hey, there was no cycle. Okay, maybe these conditions are redundant here, but it's okay. This is the main crux here. This is our basic depth first search. We didn't do anything yet. So one thing I need is visited array. By default, every vertex is in 0 state, which means not visited. This I need n number of times. What is n? N is length of the given array graph. Like it said, these are the vertices. Basically, they directly gives the adjacency list. I'm just defining it in the way I want it. So I'll do self.g is graph. This you can ignore. Cool. Coming back, for every I'll say v in my vertex, so which is range of n, so this gives me 0 1 2 3 4 5 6 up till n minus 1, 0 to n minus 1. So here, if this visited of v is still 0, if it's not done, then just call DFS of v. Okay, that's what we said. And then let's just create an answer. I don't need it to be the member of class, so answer is an empty array for now. For let's just run the same loop again. For every vertex in the graph, we will simply check if it completely explored. So if self.visited of v is equals to 2, that means I can do append it into my answer. I don't know if any order was required in ascending order. Okay, anyway, I'm doing from 0 to this, so it should be ascending. Return the answer. This should do. Basic cases are working. Let me see if any case failed in the past. I'll try to use that. Use this runtime error. Use this. At least I can have more test cases to test in local. Cool. Okay, so at least what failed in past is working fine. So we'll go ahead and submit it. Okay, so this was very basic depth first search to do it. Now let's just see what reversal actually change into the code. All right, so I just actually reversed the direction of every edge. So this was our original graph. Okay, and I just reversed every edge. Rest everything is same. So few things to notice here, that whatever was in the cycle, those nodes are still approachable, or you can say in access to whatever it was in access to earlier. For example, here from 5 to 3 can I still go? Yes. Via 4 I can go to 3. From 3 to 4 can I still go? Yes, via 5. So in cycle I can go, and that was the case earlier also. From 3 to 4 I was able to go directly. Now I am able to go indirectly via 5. right? So even after reversal of direction, whatever was in the cycle, they are still reachable to each other. But that's not the true for other edges. For example, from here, I was able to reach to 3, or you can say to the cycle from 1, right? But now there is no way I can reach to 1. So just after reversal, 1 is not reachable to that cycle. Okay, so this is something important to understand. This is the actually base of Kosaraju algorithm, which is the first algorithm we will learn in our strongly connected components questions. Okay, so this is the first observation. But how we are going to use it here? If from the original graph, if I build n, let's call it out degree array. So same vertex 1, 2, 3, 4, 5, 6, 7, 8, 9. From here, what is the out degree of 6? 0. Out degree of 7, 0. Okay, let's start from 1. So out degree of 1 is 2. I'm writing it here. Out degree of 2 is 2 again. Out degree of 3 is 1. Only one edge is going out from 3. Out degree of 4 is 2 to 6 and 5. Out degree of 5 is 1, only to 3. Out degree of 6 and 7 we already wrote. Out degree of 8 is 1. Out degree of 9 is 1. Okay, so this we calculated from the original graph. And now what we did is we reversed the graph after calculating the out degree. So this is my out array. All right, now let's do our topological sorting, which we were doing earlier. So what we used to do in topological sorting, that we were founding in degree. This time I found the out degree. Both are fine. Algorithm is not going to change, right? So I'm going to leverage it. So in that, what we used to do is, in my priority queue, we used to push whichever had in degree 0. So in this case, let's consider this as my in degree array, right? So I'll simply push 6 and 7 because the value here in this array is 0. And I'll start my topological sorting, which is breadth first search, Kahn's algorithm, basically using breadth first search. So first I'll pop out 6 and I'll check what are the neighbors of 6 here. So 4 is one neighbor. So I'll reduce the value of 4 by 1. So it will become here 1. And 6 is popped out. 6 is in my answer. Let's suppose I'm building an answer here. So 6 is in my answer. Now, I cannot push 4 because still value is 1, right? Now I'll push I'll pop the next element, which is 7. 7 is added into the answer. Now how many neighbors are there of 7? Is 1, which is 9. So I'll reduce the value of 9 by 1. It will become 0. That means it's safe to add it into priority queue. So I'll push 9 here. Okay. There is no other neighbor of 7. Hence we are done. For 9, first next element which will come out from the queue is 9. So I'll add it into the answer. And it is now removed from the priority queue. What are the neighbors we are having of 9? 8. First 8. So for 8, I'll reduce the value to 1. So it will become 0. If it becomes 0, then it is safe to add it into our priority queue. So I added 8 here and there is no other neighbor of it. So hence we are done. Next element we will pop out is 8. So 8 is popped out and added into the answer. Now for 8, we are having one neighbor, which is 1. So for 1, out degree value is 2. It will be reduced to 1. Okay. And hence we cannot add it here because the value is not 0. And our queue is empty. Hence our topological sorting will stop here. Okay. So after topological sorting is stopped, whatever we got into our answer is actually our answer. Now what got improved between the last approach we did and here, that we do not need to find out that detect if there is a cycle. And what we were actually truly doing into the previous approach we did, right? It was looking a simple DFS, but what we were doing is we were doing finding all the paths which were actually reaching out to any of the cycle. Okay, and we were detecting the cycle and we were stopping there. In this case, we don't need to detect any cycle. Once you do the reversal, it's very natural that that cycle exploration is not required because of the calculation of out degree numbers which we are having. Hence, just a reversal improve things a lot. Okay, this particular thing is what we are going. It's a good observation for now, I would say. Obviously, it's lucky that I found a question to show it, but this is just for observation even now, that this is improving things for us, and that is what is being used into the algorithm which we are going to learn soon. But first, let's just code this one to establish that whatever we discussed is actually true or not. Maybe it is just working for this case, but whether it is working for every case or not. All right, let me just get rid of this first. Sure. So what we said is I need a priority queue, first thing, and I need an out degree calculation. So this is an array which is having 0 by default for every vertex. I'll calculate the out degree, and n is nothing but length of the graph, because graph is an adjacency list. All right, so I can do two things: calculate out degree. So I'll run a loop for every vertex in this graph, which is the same loop. We will say for every child, because that is given here like this, right? For every child in my graph of this vertex, for child you can calculate the out degree, right? Okay, and I also need the reversal of this graph, so I'll call it reverse, which is default dictionary of list. I can use list of list also, same as what was given, but I'm used to using default of list, which is easy for me to handle. So I'll simply say for every vertex in this graph, which is the range of n, so it will give me 0, 1, 2, 3, 4. So I'll say reversal of first out degree is easy to calculate. So out degree of v will be nothing but the length of that array. So graph at v. So at graph 0, I'll get 2. That means there are 2 edges which are connected from 0. Hence the out degree of 0 is 2. So this is straightforward given, so I'll calculate. But for reversal, what I need to do, that for my child, so for 1, I need to make an edge to 0. So for child in graph of v, I'll do reversal of child dot append v, right? So I'm basically in my child, I am adding the parent, is what you can say. So this reversal is also done. Just to show if you are unable to get it, I'll print this reversal and I just return something from here for testing. What we need to return actually? Expected is an array, right? So I'll return an empty array. Okay. So if you see, what is happening is for 1, so 1 is having now edge to 0, 2 is having edge to 0 and 1. So it's the reversed graph, right? Okay, so that is what happened so far. I'll comment this line. Moving on. So what we said is we will have a priority queue, which I created here, and in our priority queue we will push all the nodes. So for vertex in a range of, you know what, I could have done it here easily. So if I define my priority queue earlier, and ultimately here if out degree of v is 0, so I can do heap for now. I can simply push, right? So priority queue dot append, because all are having like 0 only, so no need to do anything. Priority queue dot append v. Okay, so now I'm having from this one I would say this and this, so 5 and 6 will be appended into my priority queue. Maybe just to confirm, let's print that. So priority queue, if I print, I don't know why I'm debugging here, but just 5 and 6, right? These are my terminal nodes. So what we need to do is now, while priority queue is not empty, I need to run this loop. Let me also have an answer array, which is what we are going to return ultimately. So we are just doing the breadth first search. It's not Dijkstra. I confused myself, so I don't even need priority queue. I'll call it a queue. Okay, so in queue I pushed it. This is queue, and queue normally we do dq. dq dot append, I think it's fine. Yeah, now I'll do, let me call it vertex again, which is popped out. So q dot pop left answer dot append vertex for child in reverse of this vertex out degree of this child minus equals to 1. If out degree of this child is now 0, then what we will do is q dot append child. That is all we said, right? And ultimately we'll return the answer. Let's just check if we missed anything or any indentation issues. Oh yeah, this is not. Yeah, so in this case, basically the order is not maintained. So I just need to, I got the answer, it's just that I need to sort it. So there is one way we can sort it, or another way could have been, if I want to do it in linear, I can say by default every node is not safe. So let's call it whether it's safe, mark it not safe for every node first, and when I'm coming here I'll mark it as true. So safe for vertex is true. This is another way of doing it, I would say. And now I will compute my answer. That answer is, you can say, an empty array, and for I in a range of n, if safe I, then simply append answer dot append I. This time it will be in sorted order by default. So if I run it, this should do. Let me just submit it. Perfect. So I'm not going into the time complexity of it, because this is usual what we did already for breadth first search and all. There is nothing different. But the key thing which I wanted to show was what reversal of graph will give us. Okay, and we will build our intuitions, these small intuitions, ultimately to solve the bigger problems. That's it in this video, I guess. Let's jump to the next section. Thank you.